Hello. So I'd like to welcome you to this little video. We're going to be talking about how Salsa works. And I'm going to be doing this by working in this Dropbox Paper document, the URL for which I will post with the video. And you can come later and kind of look at it if you like. So let's start with the first question. What is Salsa anyway? Salsa is a library for incremental recomputation. And what I mean by that is basically imagine you have some function like, we'll call it foo, very creative. And it has, let's say, two inputs and it produces an output. And these types, they might be of type A and B or something. And the idea is, well, in some part of your code, you invoke this function with one input. And then later you invoke it again, right? But with a slightly different set of inputs. Maybe A is the same, but B is changed. We would like to make this more efficient. We'd like to reuse some of the intermediate values that we did right, in the first call. And that's the basic idea of Salsa, is how to make this kind of automatic. And what I mean by that is we will reuse automatically. I don't necessarily mean that you'll get really good reuse. That requires you to do some tuning. But we will reuse automatically and sound or correct. And by that I mean you get the same result, essentially, as if we didn't do any reuse at all. Okay, so cool, that's what Salsa is. Now, so Salsa's actual model isn't like a random function like foo. It's actually needs to handle much more complicated cases, right? So imagine you have like an IDE. In that case, you might have, the inputs might be something like a manifest. You can think of like cargo.toml file and the data inside that maybe, as well as the sources, like the source files and their text, right? So it might be like, okay, foo.rs has, this is the contents of foo.rs and so on. And the outputs, well, there's a lot of possible outputs, right? One might be the actual like binary executable that you want to run, but you might also have things like, what are the completions at this point? Or what is the type? Or what should I show the user when the mouse is hovering on this line? That sort of thing. So there's a kind of rich set of inputs and outputs, not really a single function. And that's kind of more the model that Salsa is working in, right? So let's give a kind of high-level idea. So how does it work? What is the kind of high-level view of how Salsa works? Well, you're going to identify, the first thing is you have to identify for yourself those inputs and outputs that you want, right? And when well, rather, you identify the inputs that are like, let's call them the base inputs to your computation. And the main thing here is that they are not something which you compute, they are something which you kind of get set from the outside. You kind of get given them. And then you have these things which are kind of derived values. And derived values are basically some deterministic, you're going to give a deterministic kind of pure function from the inputs that computes them, right? And this function will start with some of the inputs and produce the outputs. So these derived values, they might be, at the very limit, there'll be things like what are the completions at this point, but there might be intermediate steps. So let me give you, so if we come back to our IDE example, if the inputs are things like the source text, the manifest plus the source text, then some derived values might be like, for each source file X, we might have a derived value, the AST for X, right? And so actually we're going to express the manifest here as like, you can think of these as like a label and maybe some inputs, right? So the source text might be like, kind of give me the source text for some path X. And the manifest, just to keep it simple, maybe the manifest actually gives you back like a vector of paths. And the source text would be like path X, and it'll give you back a string, let's say. That's kind of how these are going to look when we eventually get them into Rust. There we go. So our AST might be something like X, the same path, and it's going to give us an AST, whatever that is. And so an AST is not like a final output. It's an intermediate value that we would use, right, to do our computation. And eventually we'll have something like the completion at line number and column number, whatever. And this would be like if you what the IDE should show. And so what's going to happen is when you go to execute, say, what is the completion, we're going to see that it's going to compute various derived values as it goes, intermediate values, and eventually read from the inputs to produce the result. And Salsa, the framework, is going to track. So in the course of computing, say, the AST for a given path, we'll track which inputs did we access, which derived values, and we'll use that later to figure out what should happen when the inputs change. Right? So when an input changes, we can say these derived values are still valid because none of the inputs that they touch changed. Or maybe these derived values may be invalid, right, because some of their inputs changed. And we'll see that actually we're a little bit smarter than this might suggest. So it doesn't just figure out everything that's sort of downstream from a changed input, because that would usually be quite a lot of your computation. We can actually do somewhat better than that. Right, so, but basically the model the model that it's useful to have in your head is there's a kind of graph. So we might have, we have our inputs on one side, right? So let's say something like this. And then these are like, we call these queries. These are the nodes in the graph. Right? And then when you have a derived query, so something like AST, I'll do the edges this way, these become also nodes. And so what we're saying here is when I'm computing the AST for a given path, I need to know I'll have to use the source text to do it, and then I'll invoke the parser. Right? And maybe computing the AST is just running the parser on one file. It doesn't need any other input than the source text. But how do we know? So this is all in the context of some compilation, right? So somewhere there'll be some sort of some root thing that we're trying to do, and this is kind of that function foo I was talking about. And this compilation, maybe this is going to read from the manifest to start, and it's also going to read like from each of these. Once it reads from the manifest, it's going to go access it's going to go read the ASTs of all the inputs, right, and so forth. Actually, of course, there'd be a lot of other intermediate values between the ASTs, but let's just say that the rule of compilation is just to parse, basically. Maybe we can rename this to like parse everything. So now we have kind of our base inputs, the manifest, the source text. These are our base inputs. We have some intermediate derived values. And then we have this goal here, parse everything, or maybe we'll call it whole program AST, just for fun. And we'll say the whole program AST is all the ASTs for each file concatenated. And in order to compute that, we had to access the manifest. We had to access the AST for each individual file. And then we gave out a result. And maybe this winds up being computed part of like type checking or something. Actually, this wouldn't be a very good structure for intermediate reuse, but we'll come to that later. And so now, when we have this graph, if we see a change, like the source text, then we can easily see, okay, if you change a.rs, that's going to potentially affect the AST. That will in turn potentially affect the whole program, which would mean type checking. All these results are invalidated, but the ASTs for the other files, they're just fine. Okay? And one of the cool things also is able to do is actually stop this propagation a little bit early in some cases. And so imagine that although we see that like this whole path is potentially affected, this whole path here, we might also see that after we rerun the parse, we wind up with the same AST we got the time before. Right? So maybe all they did was add some spaces, and that doesn't affect the AST. So then although the source text changed, the AST stayed the same. So then we can wind up keeping these values because we say their direct inputs did not change, even though some of their like indirect inputs have changed, but it didn't make any difference for our purposes. We'll come back to that. But that's a pretty important concept. So, all right, let's go just a little bit deeper. I'm going to talk now about the idea of actually kind of show you how these salsa concepts work out in practice. So there's a few key concepts to keep in mind. The first thing is something called a query. Let's do it like this. Right? And a query, we've actually been looking at queries these whole time. So when I write like, manifest, this is an input query. And when I write whole program AST, this is a derived query. And both of these queries have, a query is basically some value that we access in the course of our computation. It might be something we compute for a derived query or something we're given for an input query. And queries in general have some number of keys. Both of these have 0 keys, but something like source text path, that had one key, which was the path. And all queries, which I didn't write initially, have a result type, right? So they're kind of a function. So this would be like a manifest. This might be an AST. The source text, I think we said, was a string. And the AST, that's just for completeness, we'll throw in the AST. It could also be an AST, right? So these are derived queries with one input and one output. You always have one output. You can have any number of inputs. And so we don't have any good examples here, but you can have a query that's like, takes 2 integers. And now it kind of has 2 keys, or you can think of it as it has one tuple as the key. Right. And the output here would be like, let's say F32. Great. Okay, that's what a query is. And the next key concept is something called the database. So Salsa database is going to be a struct. It's basically the context for your entire computation. It's going to store all of Salsa's internal state. You can also store other things, whatever you want, basically. And you should be a bit careful because you can mess up the incremental results if you have shared mutable state in there, or mutable state. But it's going to store Salsa's internal state, and it has essentially all the intermediate values for these different queries that we might wind up reusing when we recompute. All those intermediate values are things that are stored somewhere in this database. So basically, the database is kind of like it's kind of the heap for your Salsa computation, all the data that you need. Now, the only thing is, just like you don't build your whole program in one giant file or one giant function, you don't build your database kind of all at once, right? It's going to have to, because it has all the internal state, it has to know all the queries that you will do, basically. But you don't have to list them sort of all in one place. Instead, what we do is we group queries into what I'm calling query groups. They're kind of like Salsa modules. And they're basically a set of queries which you define together as a unit, and then you combine query groups to form your database. I'll come back to query groups, but I want to just point out one other thing. The way you're going to interact with Salsa, when you have these queries, the database basically feels like a function of the database. So, for example, if I have a database and I invoke db.manifest, I get a manifest returned to me, right? And then the idea is, or if I invoke db.ast something, then I'm going to get the AST returned to me for foo.rs. And the idea of incremental recomputation is that these values are memoized. Right? So if I invoke this twice, I just get the result cloned. I don't recompute it, at least by default. That's something you can alter. And the idea is, even once the inputs change, I may just get the result cloned. Right? So if this is a result that was not affected by the change to the input, I can just get it cloned. I don't have to recompute it. So how do inputs change? Well, when you have an input query, you also have a method, a set method that you can use, where you kind of say, okay, I'm going to set set the value of this input. And this triggers other memoized or previous memoized values to be potentially invalidated, like invoking set. So it changes the inputs. Okay, so let's come back to query groups. So we saw now how you're actually going to use the database, but how are we going to define the database? We're going to do that using query groups. And the idea would be, let's use an example. We'll go back to our IDE queries here to do it. We might want to have, for example, a query group that is basically the core inputs. We'll just call it inputs that I've identified, right? And to do that, we just basically write a trait definition. We set the starting point. And we're going to apply I'm going to use these types for now. These actually would be rather poor choices, I'll explain in a second. And we're going to apply this Salsa attribute macro called query group. I'll explain this name in a second. And what this will do is it's kind of a decorator or attribute macro. It will process this trait. It will produce that trait as output, but it will also produce a bunch of intermediate stuff that Salsa uses. And one of those things is something called the storage struct, the name of which is given here. And this we'll see later. We're going to use that later when we create the database to put all the query groups together, right? And so basically the set of queries in the query group are just the set of methods in this trait. All the methods have to have a form much like this one, ampersand self, and so on. And you can mark them with special attributes like Salsa input to indicate that, in this case, we're saying these are the base inputs. So if you have for every input, we're also going to have a setter as a member of the trait, which is auto-generated. Okay. So now we've defined a query group. And the key point of this query group is this is like a set of standalone queries. In this case, they're all input queries that we can define. And we could define another query group, perhaps, for the parser, let's say. And it's going to look much like the one we did before. But here, we might say, okay, function AST. So we said that now we're defining this AST query, let's say, right? And oops, ampersand self, it's okay. So now we've defined this AST query, and if you recall, I showed you before, the AST query is going to wind up, when it executes, it's given the name of the path to parse, and so it needs to get the source text for that in order to parse it. So you can make one query group have access to another just by linking the traits together. So here I had a trait inputs, and now I say, well, the trait parser extends inputs. And this query AST is not an input query, it's a derived query. So we have to give the definition. And you can do that just by writing a function. You write it outside of the trait definition. And it should look something like this, right? And this is just ordinary code. Yeah. Well, sort of. Yeah, it's just ordinary code. But so this is the function that when we do need to recompute the AST for a file, we're going to call this function. And we're going to give it the database. Now, we don't know all the query groups that are part of this database. So what we get is actually some unknown type, and we can use infiltrate to kind of say, well, this is some database that implements the parser trait. And because it implements the parser trait, we know it has an AST query. We also know that it implements the inputs trait, which means it has a manifest and an input file query defined as well. So now we can do stuff like, we can get the source text for a given input file. And actually, I think, yeah, sorry, I changed names. Made edit here for some reason. So let me just patch that up. So we can get the source text for a given file by calling dd.sourceText. And now we might like do the actual parser on source text, and we would return the AST, right? So that's how you define a query in Salsa. And also, I just want to point out, this is using infiltrate. You could use dimtrate. It doesn't matter. I actually like using dimtrate better because then you won't generate as many copies of this function, or you will generate the code. It kind of helps with compilation time. But okay, now we have this Salsa group, and we can keep building these layers as high as we want. right? So maybe maybe we want to put this whole program AST perhaps belongs with a parser. It kind of feels like a parser. Oops, this should have been AST. It kind of feels like a parser activity. So we can put it like so, and then it might say sort of or source file in db.manifest. Let's say let's use AST as AST default. I don't know. I'm just kind of making something up here. Whatever. So the idea here would be we iterate through the manifest. We create. We get each source file. We get the AST of the source file by invoking the AST query, which we'll call this code, and then we kind of put that into this master AST and return that. And this is the whole program AST. So this is kind of how you define a group of queries. There are ways to take these functions. If you don't want them to be in the same module with the tray is defined, you can change that. But now, finally, then we can layer this up even further. And so maybe our type checker, remember we have this type checking idea. That might be kind of here. Type checker storage. So that will build on the parser, and it will have a type checker query. Right. I don't know, maybe this returns a vector of errors. That's the basic idea. Now, when you're all done with this, eventually you do have to define, so this is how you define all the little modules, but then you have to put them all together to make your final database. And the way that looks is that you make a struct, and in that struct, you annotate it with Salsa database. This invokes another query. And what you're going to list here, this query takes as input all the storage for each query group that you need. So for every query group that you want to put into this database, you have to have its storage. And so we put them here, and you have to have this one field, which is a Salsa runtime. And you have to implement the Salsa runtime, the Salsa database tree for your database type. Let's call it my database, just to make it clear. And implementing this trait isn't actually very hard. All that it has, if I recall, in terms of mandatory methods, is a single method which returns to the database. This is basically how this. So what happens here is inside this runtime, we're going to generate the storage for all of these query groups internally and manage it. And you own that storage in the end, and you have to be able to give us access to it by calling this method. And that's how you define your database. Usually what I do personally is I also derive default, for example, so that then you might have a program which says like, let db is my database default, db.set manifest, blah, 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 db.set input, or set source text, or whatever it was, blah, blah, blah. So you kind of set up your inputs, and now I could invoke this type check query, right? And then I could have a little loop that would like perhaps apply some edits and re-invoke type check a few times. And each time we're going to reuse whatever results we can from the previous execution, right? Okay, so that's the basic overview of Salsa. And thanks for listening. I would say if you want to learn more about Salsa, I will be doing some other overviews, but also you can come take a look. Here's where it is, Salsa RS Salsa. There's some stuff, there's some instructions, and in particular, there's a hello world example that kind of shows all the things I talked about, but in somewhat more detail with comments. And it's available on crates.io. Thanks very much.